y. If you were super worried that we were going back to limits and we wouldn't be dealing too much with the derivatives anymore, don't worry. We're still doing derivatives. So today what we're going to do is implicit differentiation. That sounds scary, but really things that sound scary really shouldn't be all that bad, and it will help you gain more friends. That's why really popular people are really good at math. That's what I always say anyway. Okay, implicit differentiation. So it says in this one, I don't know why there's such a big space, just because, you know, word is kind of crazy. It should have been down at the bottom, but whatever. We're just going to go with it. If you want to draw a picture right here, now would be a good time. Just, you know, like picture of your emotions or whatever. This says Daily Lessons 101. I don't really know what page I'm going to yet. It just depends on how long I talk and if this is 1 or 2 videos. Much of our algebraic study in mathematics is dealt with functions. Okay, yes, so lots of functions. F of x is equal to something. It says in pre-calculus we talked about something, but we didn't talk about anything because I wasn't your pre-calculus teacher. But that's okay, you probably did. And they're explicit and implicit functions. Explicit functions are not functions that involve swearing. Although, in some of them, if they look really bad, you might, but I'm hoping not. Explicit functions are just where they're solved for y. So y equals 3x plus 2 is an example of an explicit function. It's explicitly solved for y or f of x. Implicit, y is somewhere within the problem. So for instance, y is equal to the square root of 25 minus x squared. This is an explicit function. It's explicitly solved for y. Whereas, there's a plus or minus, that's fine too, if there's 2 y values, but this is explicitly solved for y. Implicit equations are very different. So it might be something that looks like this, for instance. You see how you've got y squared and a y mixed within the problem? And even there's some functions that you could solve for y pretty easily. This one, you can't. X squared plus y squared minus 2x plus 4y plus 16. It's really hard to isolate y. This is an implicit function. And you're thinking, I can't take the derivative of that. But you can. Yes. So we'll utilize the alternate definition for the derivative. So instead of f prime, we're going to be using dy dx. So Leibniz for the win on this one. As calculus was developed by 2 different men, a blend of their notations has been accepted. And this is true all throughout every unit we do. We use the one that suits our needs best. In this case, the dy dx is preferable, and you'll see why. So here what I'm going to do, let's think about how we differentiate this function. And I'm actually going to use the space at the top. And I'm going to say, you know what, I know y is, instead of square root, I'm going to write 25 minus x squared to the 1/2 power, because this would be the same thing. And then if I take the derivative, so dy dx, this is the change in y over the change in x, or slope of the tangent, so dy dx is fine. 1/2, leave the inside alone. My new exponent is -1/2, and then I'm done. No, I'm not. That would be silly. I need to multiply by the derivative of the inside because this is a function within a function. Wow! Which means you need to use the chain rule. So multiply by the derivative of the inside. I'm going to rewrite this just to make it nicer. Dy dx is equal to -2 times 1/2 would just be -1. And I could just say -1x, or I should have said -x, but it's fine. I'm going to keep it like that. In the denominator, I would have 25 minus x squared raised to the -1/2 power, or I could say, oh, sorry, as soon as I move this to the denominator, it would be +1/2 power, or I could say the square root of 25 minus x squared. Okay, so this is the old way. This is an explicit function, so I just did this, took the derivative the way that I know how. Let's go down here. And now I've got x squared plus y squared is equal to 25. And if we were to actually solve this on the side, x squared plus y squared is equal to 25. 25 minus x squared. Take the square root of both sides. You can see this is actually the same function either way, but this one is defined implicitly. So the y is not solved for. So I'm going to go x squared plus y squared is equal to 25. And what I'm going to do is something a little bit crazy, but normally, even in these ones, we took the derivative of the left, just the derivative of y would be dy dx. And then we took the derivative of the right-hand side of the equation. We're going to do the same thing down here. The derivative of x squared, we know, is 2x. The derivative of y squared, you might think, is 2y. But this is a little bit strange, and this is really the major thing that you need to know for everything else within this whole section, is that when you take the derivative of y, the derivative of y we set up here was dy dx. And the reason why we don't have to do this with x, we don't have to say dx dx, is because the change in x over the change in x would just be 1. So instead of writing 2x dx dx, we just write 2x. Here I'm going to say 2y times dy dx. What really is going on here is the chain rule. I'm taking the derivative of the outside, wow, leaving the inside alone. So this would be 2y times the derivative of the inside. The derivative of y is dy dx. That's the trickiest part. Anytime that you have a y, you have to multiply by dy dx. That's another way to remember this. The derivative of 25, any number, is 0. And now what I'm going to do is I'm actually going to solve this and get dy dx by itself. So just like you would have in Algebra 1, subtract 2x on both sides. And then I'm going to divide by 2y. And I'm going to say, you know what, this 2 divided by 2 is just 1, so I would have negative x over y. And you might be thinking, didn't you say this was the same function? You know, like if I took x squared plus y squared is equal to 25, and then I took the square root of both sides. These two things should have been the same function, so their derivative should have been the same. And this doesn't really look like this. But there's more. dy dx is equal to negative x. Instead of writing y, oh sorry, I should show you down here. Instead of writing y, remember how y is actually equal to square root of 25 minus x squared. We can see it over here. Square root of 25 minus x squared. Ta-da! That derivative matches this derivative. You get the same thing. So even in implicit differentiation, the derivative still is the slope of the tangent. It just looks a little bit different because y is within the problem. That's okay. And now we're going to see on a graph how this actually looks like slope of the tangent. So what I want you to do is go to the next page, and you're going to see a circle there. This isn't something I'm going to test you on later or anything, but just to remember, whenever you have a circle, the formula is something squared plus something squared. So like x squared plus y squared is equal to the radius squared. In this case, the radius of the circle, if I see the center is right here, the radius is 1, 2, 3, 4, 5. 5 squared, also known as 25. Over here, instead of it just being x squared, because I can see that the center of the circle from the origin was moved 1, 2, 3 places to the right. This is one of those, if you remember, that you have to go the opposite, x minus 3 squared. From the origin, I can see that I go down 2. So you should have y plus 2 squared. And again, if you don't know this, it's okay. What you do not have to do, it says now implicitly differentiate the equation of the circle. The old way, what we would have had to do is would have had to square both of these. So actually take x minus 3 times x minus 3, y plus 2 times y plus 2, solve for y, and then it just would have been this whole mess because I would have had y squareds and y's. I don't want to do that. What I want to do is implicitly differentiate. So if I do that, I'm going to take the derivative of the first. So I have a function within a function. Wow. You have to use the chain rule. So I have 2 here. My new exponent is 1. I leave the inside alone. Times the derivative of the inside. The derivative of x is just 1. Plus, same thing over here. I have 2. I leave the inside alone. My new exponent is 1. So I'm leaving the inside alone. Times the derivative of the inside. The derivative of y is not just 1. Remember, we're differentiating with respect to x, so we say times dy dx. What's the derivative of 25? It's 0. It's not 25. So the derivative of 25 is 0 because this is just a constant. So if you think about y equals 25, what's the slope of the tangent for that line? It's just going to be 0. The next thing you need to do is get dy dx by itself. So I'm going to say 2 times the quantity y plus 2 dy dx equals, and here I was going to subtract this on both sides. negative 2 times quantity x minus 3. Divide. And I can see I get a derivative, dy dx, that is x minus 3 over the quantity y plus 2. And actually there's a negative in here because this is negative. And if you wanted to change that right away to negative x plus 3 over y plus 2, you could. But you don't have to. You could just leave it like this. Okay, so this is the derivative. We did it. Nothing crazy. You get to use all the rules that you knew before, and now just translate it here. Really, the one that you use the most is power rule and chain rule when you're doing implicit differentiation. So this one says, complete the table below by finding dy dx, so finding the derivative at each of the indicated points. Then draw the graphical representation, I can speak, the tangent line on the graph at each indicated point. So remember dy dx is the slope of the tangent. Let's see if that still works. It does work. Okay, dy dx, and I'm going to say at 0, 2. So the derivative at 0, 2, I'm going to substitute in 0 for x. So I'd have 0 plus 3, and 2 for y. And I get 3/4. If I go and check on my graph at the point 0, 2, because the tangent line will touch a graph at exactly one location. Hey, there it is. I can see that I'm going to have a slope of 3/4. 1, 2, 3, 1, 2, 3, 4, because I'm just doing rise over run. Or I could go down 1, 2, 3, 1, 2, 3, 4. What? That's amazing. We just created a tangent line. Let's do the other ones. So the next one, dy dx, this time at 3, 3. So I'd have negative 3 plus 3, 3 plus 2. Oh no, I get 0 over 5, which is just 0. How can that be? Let me go up to my graph. At 3, 3. Ooh, this is nice. A slope of 0 is going to look like this. And that's okay. So this one has a horizontal tangent and x equals 3, or I should say at the point 3, 3, because x equals 3 could be here or here. So this is technically not a function because I don't have one output for every one input, or one input. It doesn't have exactly one output. Okay, the next one, dy dx, 8, negative 2. This would be negative 8 plus 3 over negative 2 plus 2, which is negative 5 over 0. Oh man, I don't even want to put an equal sign. What does that mean? This means undefined or does not exist. Let's go check out and see what this would mean on the graph. 8, negative 2 is right here. This is my tangent line. What? We've got a vertical tangent. I go down 5, run 0, or I can go up in any direction and go over 0. Vertical tangent. So the tangent line, the slope of the tangent doesn't exist, but this is still the tangent line. The next one, derivative at 3, negative 7 will be negative 3 plus 3 over negative 7 plus 2. Every time I'm going back up to here, if you haven't noticed. That would be 0 over negative 5. Again, 0. Let me check. 3, negative 7. Oh, that makes sense to me. The slope of the tangent. So derivative is a fancy name. Slope of the tangent. Dy dx, 6, 2. I feel like you've got this, but we're going to keep going because I don't want to leave blank spaces. Negative 6 plus 3, 2 plus 2. That would give me negative 3/4. Okay, let's do this. So 6, what do we say? Oh, 6, 2. I almost went to 6, negative 2. Negative 3/4, I go down 1, 2, 3. Right, 1, 2, 3, 4, because I'm just doing rise over run. These lines are pretty good. I haven't bragged about this yet, but just saying, pretty good. Okay, next one. The next one's probably going to be awful or something since I said that. Dy dx is negative 2, negative 2. Pride comes before the fall. Okay, negative negative 2 would be 2 plus 3 over negative 2 plus 2. Oh no, I get something over 0. 5 over 0. Let's see it. Negative 2, negative 2. Oh, that 0 makes sense, like something over 0. So this tangent line exists, but it's a vertical tangent. This, I can say that the slope of the tangent does not exist. Last one. We've got 6, -6. So I'd have -6 plus 3 over 6 plus 2. And I get -3 over 8. -3 over 8. Let me just make sure I've got this right. This is at 6, -6, so -6 plus 3. Okay. At 6, -6, something's wrong, because this should be a positive 3/8. Let me check. This, my x value was 6, so -6 plus 3. Oh, that's why. -6 plus 2. We got this, everybody. We got this. This would be -4, positive 3/4. Looks so much better. And I had just checked my graph, and I knew it was going to be positive because my slope was positive here. 1, 2, 3, rise over run. 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, 1, 2, 3. Sorry, something's weird. 2, 3, 4. There we go. That line wasn't that good right after I said the other ones were. Do you want to do more? I want to do more. Let's do more. Okay, so in the next page, we get to practice this. It says find dy dx. So find the derivative for each of the following implicitly defined equations. So I'm not even trying to get y by itself. All I'm doing is going to the derivative right away. So the derivative of y squared. Think about it if it was an x squared. You would get 2x, or in this case 2y. But the derivative of the inside, chain rule, wow, would be the derivative of y we know is dy dx. Is equal to the derivative of 2x is 2 plus the derivative of 3y would just be 3 dy dx. And then you're like, oh, hold on a second, there's 2 dy dx's. What do? You get them on the same side. So anything with a dy dx you get on one side, anything with just a number you get on the other. So I'm going to subtract 3 dy dx on both sides. And you could have done this the other way. You could have gotten all the numbers on the left, this one on the right. It doesn't matter. So I have 2y dy dx minus 3 dy dx is equal to 2. The next thing you need to do is factor out a dy dx. And you get 2y minus 3 is equal to 2. To get dy dx by itself, divide. Ta-da! My derivative. We did it! Next one. Okay, this is such good practice for all the other derivatives that you're going to be doing, or that you have done, I should say. The derivative of 2x is 2 plus the derivative of e to the anything is e to the anything times the derivative of the anything. So e to the y would be e to the y times dy dx is equal to the derivative of x squared is 2x minus the derivative of 2y squared is 2y dy dx. Same idea, get the dy dx's all on the same side, all the numbers on the other side. So e to the y dy dx. I'm going to add 2y dy dx. I have a 2x over here, and I need to get this 2 to the right. So I added this to both sides. I subtracted the 2 from both sides. Factor out the dy dx. Divide to isolate the dy dx. This one I just feel like is good fun. I really like it. Okay, let's keep going. This is my derivative. We found it. And the next one, 2xy. Wait, x times y? That seems like a product rule to me. Hooray! It is! You don't always get to do product rule on these, so it's a fun time when you do. So the first one is 2x. So first, what is the product rule again? First times the derivative of the second. The derivative of y would just be 1 dy dx plus the second times the derivative of the first would be 2. Then I go to the other side. 3y squared would be 6y dy dx plus 2. Get dy dx's on the same side. So I've got 2x dy dx I'm going to subtract 6y dy dx. This was a positive 2y, so to take it over to the other side, I'm going to have negative 2y. Keep the 2 on the same side. Factor out a dy dx. Divide. You could keep it like this. If you said that you really wanted to factor out a 2, just make sure that you do it correctly. So dy dx, if I simplify this a little bit, I could factor out a 2 and get negative y plus 1. Again, be careful with simplifying anytime that you do it. X minus 3y. If you get the dy dx on the other side, you're going to get the exact same thing as me, except every sign will be switched. So this would be a positive y, a negative 1, and negative x, a positive 3y. And then you get the same solution overall. Next one. Sorry, I'm very popular. I'm getting emails. They must have seen the math that I was doing. Probably. Okay, 5x to the third would be 15x squared. The derivative of 3 is 0. The derivative of 2y is 2. dy dx. Ooh, product rule. Yes. First, the derivative of the second will just be 1 dy dx. Plus the second, be really careful about the negative here. The derivative of the first is negative 6x. Get the dy dx's on the same side, everything else on the other side. So I'm going to say 15x squared, and I'm going to add 6xy to both sides. I just rearranged the order a little bit because this is y times negative 6x, but I'm getting it to the other side. And then I've got 2 dy dx. See, I'm so popular. Negative 3x squared dy dx. I'm going to factor out the dy dx. And then I'm going to say, okay, well, on both sides, I'm going to take 2 minus 3x squared. And I get 15x squared plus 6xy. I don't know why I'm rewriting this one and the other ones that I didn't, because this is by itself more, but whatever. 2 minus 3x squared is equal to dy dx. If you really wanted to factor out in the numerator a 3x, there's not really any reason to do this, but if you did do this, it would be okay. This would be 5x plus 2y. Be really careful with doing that. Over 2 minus 3x squared. If you felt so inclined, you could do that. But you don't have to. Okay, and now I have a very tough decision. Do we move on or not? Sadly, I think the answer is no. So what you're going to do on the top of the other page is say, this is Daily Lessons 101 to 103. And then I'll come back for the next video. If there is anything you need from me, please, please, please let me know. Thank you for being awesome. I appreciate you. I'm thankful for you. So much so. If you need anything at all, let me know. Reach out. I want to help. Thanks so much. Bye.